Hello and welcome to Business Calculus Differentials. Using increments, we developed an alternate form of the derivative, which looks like f prime equals the limit as delta x goes to 0 of delta y divided by delta x. If this limit exists, we may use the quotient delta y divided by delta x as an approximation for the derivative f prime whenever we have a small delta x. It's also true that this approximation works in the opposite direction, letting us use f prime to estimate delta y over delta x. If we look at our approximation from the previous slide, f prime equals delta y over delta x, we can rewrite this expression as delta y is approximately equal to f prime times delta x by multiplying both sides by delta x, assuming delta x is some small value. The right-hand side of this expression is very, very useful, and we give it a special name, differential, and giving it a special symbology, dy equals f prime dx, or df equals f prime dx, where delta x is equal to dx. Let's look at an example for differentials. We want to find the differential dy for f of x equals x squared plus 4x and evaluate dy under the following conditions. So first off, let's write our formula for dy. dy equals f prime of x dx, which, by the way, is a different version of this expression. And we would like to perform the following calculations. So let's first determine the derivative of our function f. The derivative of x squared is 2x, and the derivative of 4x is equal to 4, so the derivative of our function is 2x plus 4. Now we can start calculating dy. For part A, we have that dy equals f prime of 2 times 0.1 for dy. We plug 2 into our derivative. We get 2 times 2 plus 4, which is 8. And we multiply that times 0.1. So 8 times 0.1 gives us 0.8. All right, let's look at part B. We're going to have that dy equals f prime of 3 times 0.1. So we plug 3 into our expression for the derivative. So we get 2 times 3 plus 4 times 0.1. This is going to give us 10 times 0.1, which is equal to 1. And then lastly, for part C, we calculate dy equals f prime of 1 times 0.02. Plugging 1 into our expression for the derivative, we get 2 times 1 plus 4, which is 6, times 0.02, which gives us 0.12. Let's look at one more example. We still want to use our expression for dy, so let's recopy it here. dy equals f prime of x dx, which tells us that we need to determine the derivative of our function f. So let's write down f prime. From a previous lecture, we recognized that the square root of x is equal to 1 over the square root of x, and the derivative of a constant is 4. So we just write plus 0 or leave it alone because it doesn't add anything to our result. Now we can start calculating dy. We get that dy equals f prime of 4 times 0.1. So we get 1 divided by the square root of 4 times 0.1. The square root of 4 is 2, so we have 1/2 times 0.1. And 1/2 of 0.1 is 0.05. For part B, to get dy, we calculate f prime of 9 times 0.12. We get 1 divided by the square root of 3. Sorry, the square root of 9, which is equal to 3, excuse me, times 0.12. So we have 0.12 divided by 3. And we know that 12 is evenly divisible by 3, so this tells us that our result is 0.04 for simplifying this expression. All right, to give ourselves a little bit more room, let's do part C on the other side of the page. We have dy equals f prime of 1 times negative 0.01. That's fine for dx to be negative. We plug in 1 to our derivative, so we get the square root of 1 times negative 0.01. Square root of 1 is 1, 1 divided by 1 is 1, and so we are left with negative 0.01 as our value for dy. Alright, using what we've just discussed, I would like for you to evaluate dy in the following situations for f of x equals x cubed plus 2x minus 1. When x equals 2 and dx equals 0.2, when x equals 1 and dx equals 0.1, and when x equals 1 and dx equals 0.05. Here are some potential responses. And thank you very much for listening. I'll see you next time.